today we're going to be talking about pushdown automata. Now, before I could get into a definition, I think it's a good idea I give you a feel for what a pushdown automaton is. I think what will help do this is connect it to things that we've already discussed up to this point. So what we're going to do is we're going to let us consider a more descriptive, meaning that it's able to describe more languages. That's a little bit of a spoiler. More descriptive finite automaton. With two main ideas. So I'm just going to switch markers here. So the two main ideas are going to be, one, well, we know it's going to be involving a finite automaton. So this is going to be something that's going to use this aspect of a finite automaton, but we're going to add a couple more features to it. So we're gonna beef it up. That's not a technical phrase, I just think it's fun. So I'm gonna beef up the finite automaton by giving it the ability to remember things. So the first part of this will be that I'm going to use one of the more versatile finite automatons that we had seen previously. So can anybody recall, so we've seen a few different kinds, right? We've seen a deterministic finite automaton, we've seen a non-deterministic finite automaton, and we also seen a non-deterministic finite automaton with epsilon transitions or epsilon moves. So what I'm going to do is, because the epsilon moves and the non-determinism give me a lot more versatility for how I can design these machines, I'm going to use that as our starting point. I must stress that that starting point does matter in this case, but I'm going to actually start off with, so we're going to start off, imagine I give you an epsilon NFA, and I'm going to introduce to it a stack. So we're going to give it a stack. So this stack can store strings of what we'll refer to as stack symbols. Stack symbols. So I'll give you a little picture just to give you an idea of what we're looking at here. So you can imagine you have what we had as our finite automaton, which you could think of as finite state control. So it's just a finite state control. It takes in input, and it accepts or rejects, right? So that's what you would expect with a finite automaton, right? So it's going to transition from state to state. It's going to do stuff with the input. Namely, it's going to read the input. We'll describe it in a somewhat different way when we talk about a pushdown automaton. But the aspect of this that will differ now is I'm going to allow the automaton to have some form of a way to remember things. And this is what the stack is going to be used for. So the stack interacts with the finite state control. So this is going to be an integral part of how this PDA, pushdown automaton, is going to operate. So there's going to be two aspects that are going to make this a little different. The first one is that we're going to have the stack, but the stack is also going to interact with the states of the machine. So this stack idea, so the reason why I'm bringing in the stack is, so this stack can allow the automaton to, and I'm going to use the word remember because I'm just adding some agency to a machine that for which does not have agency. But we can allow the automaton to remember as much as we like. So we can, if we need more memory, as in to store this stack, we have it. Just please keep that in mind. So you might ask, Dan, what exactly is a stack? So before we get into talking about this, I need to make sure we're all up to speed what a stack is. So a stack, you may have been introduced to this idea of a stack in, say, a data structures course. If not, let me talk a little bit about it. So you can imagine we're going to have these stack symbols. So what we're going to have is we're going to start off with a start symbol on the stack. So we're going to start off with something on the stack. That's just a design feature for how we're going to define our PDAs. It doesn't have to be that way. So imagine I have this plate. So we can, of course, stack plates up, right? We can have a stack of plates. So, of course, a stack, you can place plates on the top of the stack, right? You can place plates on top of the stack, but you can also remove plates from where? Where do you remove plates from? Well, typically, if it's you imagine this is a big, heavy stack of plates, usually you remove them from the top of the stack, correct? So what I want you to do is imagine this is how we're representing this memory of sorts. And remember, for those that are a little bit more in tune with the idea of a stack and how it interacts with memory, with programs, a stack gives us versatility for things like function calls and other things like that. So with that being said, you can imagine that I have it where I can push the plate onto the top of the stack. I can take a peek at the top of the stack to see what it looks like. But in addition to this, I can also pop or remove from the top of the stack. That's going to be how the rules play with the stack, is that it has to be that we're taking elements, we're placing them on the top or removing from the top of the stack. The stack may become empty, however, if I remove the bottommost plate eventually. So remember that we can push plates onto the top of the stack. So for example, if I have just this plate, I can pop this and now the stack becomes empty. So the stack could be empty or not empty. We can push stack symbols onto the stack via push operations. So I could push this plate, I could push this new plate, I could push this plate, but I can also pop. But I pop from the top of the stack. That's what a pop operation is. So to make this a little easier for us to remember, think of a stack of plates. We can push, but most certainly we can also...
It's poppin' time.
Yeah, it's poppin' time. You can also pop from the stack. So to help us remember that if we need to pop from the stack, I brought this lovely button here. So if ever we need to do popping, it's
poppin' time.
Yeah, it's poppin' time. It's poppin' time. So that's how a stack operates when it comes to how it will for this push-down automaton. But it also is just, this is something that appears very often in places such as in data structures. It's not a coincidence that it'll pop up here as well. For those that are a little in tune with computers, like I said, you might have the idea that I mentioned just a moment ago. So this is actually giving us a lot of computational power by introducing a stack. So this is allowing us to have some form of memory of what's happening at a given state. So this actually gives us some versatility now for designing the automata beyond just having a finite number of states. Now we also can have it where we can actually take a look at what the top of the stack looks like. So all of our actions now are going to be related to both the state and also what the top of the stack might look like. So those are going to be conditional in relation to how we look at the input. When it comes to the stack, so I'll just give you a recap of what I just summarized here. So this finite state control over there, it reads the input, one after another, just like you know about, so this is what the finite control does. It reads the input one after the other, but here's the idea, is it's going to be that you can have it where it's going to, as I'm going to mention in a moment, it's going to try to consume a symbol. So it actually can make moves on epsilon, which means it's not actually consuming a symbol, akin to what we talked about with the epsilon NFA, where it could freely move. Same thing can happen here. So just keep that in mind. I'll mention this in a moment. But I must stress that on transitions, so we can peek at the top of the stack. Top of the stack. We can push or pop stack symbols. And of course, these transitions are going to depend on the current state. The current state, an input symbol, so the one you're currently looking at, possibly. Input symbol. And the top of the stack. So I must stress that it will be able to freely move on epsilon. But just keep in mind that the two big things that are going to matter a lot when it comes to definition for the PDA is its state and what's going on with the stack. As long as you remember those two details and how they can operate with independent of each other, then you're in a very good place. Is that clear, everybody? So when a transition happens, that he was looking a little sad. So what it does is it processes or consumes, I like to call it consuming, consumes from the input the symbol used for the transition. And I must stress that no input symbol is consumed. Is consumed or used if epsilon, the empty string, is used for the input. So when it does this, it might move on epsilon, it might consume a symbol. So just think of this consuming a symbol just like it's reading the next symbol. Just like we had when we talked about our finite automaton in the past. So upon doing this, it moves to possibly a new state. So it can transition to another state. Then something else happens. And this is something that makes it different than things we've seen up to this point. So something else is going to happen here. So maybe I'll number these. 1, 2, 3. So what the third thing it will do when a transition happens is it's going to what's going to happen is it's going to be replacing, or it replaces the symbol at the top of the stack with some other string. with some other string. So now there's a few cases that can happen here. First, if the top symbol of the stack is replaced with epsilon, when it's replaced with epsilon, you might ask, Dan, what does it do if it's replaced with epsilon? Well, think of it like you're going to, because remember, when it says it replaces the symbol at the top of the stack, if I'm replacing the symbol at the top of the stack with epsilon, I have effectively wiped it out. So that corresponds to...
It's poppin' time.
It pops the stack. So pop the stack. Another possibility is that the top of the stack, may not change. If the string is the same as the symbol on top of the stack. Finally, we can have a push operation occur. Or even the string may consist of more than one symbol. So pushes may occur, which may correspond to pushing multiple symbols onto the stack. So in plain language, we have three things that can happen when it's taking a look at the top of the stack. It might push, it may stay the same, or
It's poppin' time.
yeah, exactly. So I wanna give us some intuition behind this. So I'll call this a design example. So just to give you some high-level view of what you can do with a PDA. So let's consider language. So we're going to consider this language. So 0 to the n, 1 to the n, such that n is greater or equal to 0. So how can we use the above idea? So how can we use the push-down automaton? So how can we do that based on what I've just described over here? So, just as a reminder, is this language regular or not regular? Could somebody tell me? I also will mention that we've also seen how we can design context-free grammars for this language. No, it's not regular. So most certainly a DFA or even an epsilon FA cold turkey won't be able to craft some way to describe this language. So that being said, think about it like this. So remember, we have the stack. So remember, we have a stack. And we also have states, right? We have states that we can be in. So our machine can be in states. And we also have the stack. Now, just for the sake of brevity, imagine we have a string that would be a part of this language. Say 0, 0, 1, 1. So notice it has equal numbers of zeros and ones, where the zeros come before the ones. So this is indeed in this language here. So what would that look like? So I want to think about this in terms of phases. So one thing that's really helpful once we have the stack is we can think about the states as almost having purposes. So when we design the push-down automaton, you can think about it like where we think about the states actually being states, as in it is not just simply a state of, oh, I just need to move to this one thing. You can also think about it like it almost has a explicit design purpose. So this is one thing we get once we get the ability to store and remember things about how we process the input. So here's a suggestion. Break it into 3 phases. So how we're going to process the input is going to be based on 3 phases. So do you notice that we have the ability to now push and pop off this stack, right? So what's one thing that you can notice right away about the form of any string that belongs to this language? Remember, it has equal numbers of zeros as it has ones. So I was going to propose that we make the first phase where it's going to read the zeros. So you can imagine that this machine, it will proceed by reading zeros over and over and over again. So every time it does this, it's going to push a symbol onto the stack. So I must stress that typically when we design our PDAs, we're going to have it where we're going to start off, just like I said over here, we're going to start off with an initial plate on our stack, the start symbol. So we're going to have a starting stack symbol that's going to be on the stack. This is helpful for other reasons that I'm going to talk about a bit more when we get towards the end of our discussion about PDAs. But for our purposes, just imagine there's this initial start symbol there, but every single time I read a 0, because most certainly you can conceive of an automaton where you would just have it where every time it reads a 0, it comes back to the same state, right? You can imagine something like this, right? We've done things like this before. But every time it does read a 0, for each one, we push a stack symbol. And we'll give it a name. We'll say X. Suppose it's X. So for example here, what I'm suggesting is that the first phase, it'll proceed by reading each of these. So it consumes each 0. It'll consume each one of these, gobbling them up. Like it's really, really hungry. This is one hungry machine. For each one of these that gets consumed, it pushes a stack symbol on top of the stack. Namely, we have X over here. So it reads these zeros. It reads the zeros. Does anybody have any ideas of what we could do with phase 2 then? So now all we have left, what's left to consume? So one thing that is often helpful when you think about designing these push-down automata is think about what the form of the string has to look like and try to take advantage of the structure that string has when you're coming up with this PDA. So what can I say about the stack if the string belongs to the language? What should the stack look like when I'm done? What should it look like when I'm done? Should there be any X's left on the stack when I'm done processing this input? Well, naturally, Yeah, no, there shouldn't be any X's left. No X's. So naturally, if you look at how the stack works, it's actually what we're doing is we're keeping a count of how many zeros we've read. Does everybody see that? So the number of X's that appear on the stack is the number of zeros. So for every single zero, I need to do what?
It's poppin' time.
Pop it. You got to pop those X's. That's what phase 2 is going to do. So we're going to move to read ones. And then what we're going to do,
It's poppin' time.
we're going to pop the stack of a X for each one read. So if I were to consume next 1, what happens?
It's poppin' time.
Right? That gets popped. And when I read this symbol, next, consuming it,
It's poppin' time.
that goes away, and we're left with just our start stack symbol, right? Our starting symbol there. So that naturally gives us a third phase, the one where we check if no X's are on the stack, we're going to accept. So of course this is under the assumption, assuming no input is read, not recognized by the automaton, it's going to accept, right? If it does not have this form, you would reject, right? So this is under the assumption. This is an assumption I'm making. Otherwise, you would reject, right? So just as an example, suppose we had this string where we have 3 zeros, then a 1. Or actually, let's do something really funky. Let's do something really funky. Actually, now let's go with this. Keep it nice and simple. So if I had this string, it would push, push, push for the first 3 zeros, and then it will pop that 1, right? And notice that I have an X on the top of the stack. Notice that that's actually a condition for which I know that if I use this setup, that there is an equal number of zeros and ones. Do you notice that the reason why we don't have to worry about strings that look like this, for example, where I have a 1, then a bunch of zeros, you notice that I read zeros first, right? So notice it doesn't say read ones. So if I run into a 1, you know you're already in trouble because you should start popping, right? You'd start popping. But what would happen in that case? If you didn't run into any, you're not going to be popping X's, you're going to try to do something with this, right? And that doesn't make a whole lot of sense. So this is what the form would look like, right? So that's one thing I want you to keep in mind when you think about designing the PDA. So you can think of these phases just like states. So hopefully this gives you an intuition for how we're going to use the PDA. So how a PDA will work. So we're going to go into more detail about how that processing does occur with something called instantaneous descriptions. But first, I'm going to now define what a PDA is. So hopefully that's clear, everybody. So we have this idea that we can have states, and we can use the stack to help us find out what's going on. Did you notice that when I came up with this idea here for a PDA, notice it's entirely dependent on the top of the stack, right? That's important. So I'm peeking at the top of the stack. Because that's how I remember things, right? It's because it's on the top of the stack. I can peek at the top of the stack. So let's define now a pushdown automaton. PDA. I warn you that this is easily going to be one of the most complicated of the types of automata that we're going to be seeing in this lecture. So it's a little bit more of a mouthful, so please bear with me. So a PDA, P, is a 7 tuple. So we've upgraded now to a 7 tuple. And don't get the wrong idea. Just adding more tuples doesn't make the model more sophisticated in terms of its descriptive power of languages. We'll see examples of other ones where they don't have as many tuples or they have maybe the same number. It's just a formulation. So it's going to be a 7 tuple. It's going to have Q. You might guess what some of these already are. Q, sigma. We're going to have gamma, delta, Q0, Z0, and F. So some of these you're going to tell right away what they are. Others look a little more unknown to us. Where? So Q is a finite set of states, right? We have a set of states. What else do we got? Well, what do you think sigma is? What's sigma? Well, it's going to be our input symbols, right? Is a set of input symbols. Now, let's talk about what gamma is. Gamma is a finite stack alphabet. That's its name. It's called a stack alphabet. So we already know what an alphabet is, but just it's associated with the stack. That's why we call it that. So these can be pushed onto the stack. So these are the ones we're manipulating, just like in our example over there, I had X. So notice that X isn't 0 or 1. It's just that's what the stack. That's a stack symbol. There's other ones that may exist as well. Q0, you might guess quite quickly, is the start state. Now, I already sort of alluded to this, right? That what Z0 is, right? So Z0 is among the stack alphabet, or stack symbols, I'll sometimes refer to them, is the start symbol. Now, for those that are astute, may know that I've also called something else a start symbol in the past involving grammars. That's not a coincidence, just to be very clear. So the way we're going to define the PDA, you don't have to define a PDA like this, but for the sake of our designs, at the beginning, a PDA has a stack where it has only one instance of this symbol. So in plain language, the PDA begins where the stack has Z0 already on it, just like our first initial plate on the stack. So it starts off with a plate on the stack. This has design benefits. For example, we might talk about the idea of an empty stack. So this would require you to get rid of this start symbol off the stack. By doing what? Yeah, that. So, next we have, I'm going to skip over delta for now. So, F, you might guess quite quickly, is the set of accepting your final states. the set of final states. Now, let's talk about delta, the transition function. Now, of course, I should naturally tell you that if you don't use the stack at all, then you just have an epsilon NFA, right? So if you just choose not to use it for anything, you don't have to, it's just, we're generalizing, right? So lastly, we have the transition function. So delta is a transition function. Where now, instead of it being a pair, it's going to be a triple. Or three tuple for those that are keeping an eye on how I use some of this terminology. Where delta is a triple, so its form is going to be a triple or three tuple. So XAX, like this, where it's going to be a state, Q, among the states. A is an input symbol, or epsilon. And remember, epsilon is not an input symbol, just like with the epsilon NFA. And lastly, so far this shouldn't look too terribly scary. This is what we had with an epsilon NFA, right? This third part is what makes it different. Now we have the stack symbol X, which is going to be of the stack alphabet or stack symbols. Now, I haven't told you what this triple outputs for the transition function. So everything I've told you up to this point should give you an idea what is going to come out of this. So it's a state symbol or epsilon and a stack symbol. So output of delta is a finite set. So we're going to imagine it just like we had with the epsilon FA, where it outputs. Remember, it outputted a set of states, right? But I told you now that the PDA depends both on the set of states and what the stack looks like, right? So now it actually is going to be a finite set of pairs. So it's not just going to be a set of states anymore. Now it's going to be a set of pairs. P and lowercase gamma, where P is a state, and lowercase gamma is the string of stack symbols that replace X at the top of the stack. So now do you see what X's role is? Top of the stack. So whatever is going to come out of here at part of these pairs, what it's going to do is going to replace X, just like how we talked about what happens is that on a transition, it replaces the top of the stack. And those cases are now going to come up now, just a little bit more formally. So again, I'll write them like this deliberately. If lowercase gamma is equal to the empty string, what should happen if it's the empty string? So it's going to replace at the top of the stack. What did we say that means? What does it mean?
It's poppin' time.
Yeah, it's poppin' time, right? It pops. That's what we said earlier. the stack is popped. Exactly. If we have it where lowercase gamma is equal to x. So remember, that's just us peaking. So now do you see that x is really just us peaking at the top of the stack, right? So now how we define the transitions now is on the state, an input symbol or epsilon, and the top of the stack. So now, this, of course, if it's x like this, that's just the top of the stack, right? So this is exactly what we had the second case, right? Then the stack does not change. Does not change. And of course, if it is suppose that lowercase gamma is yz, then x is replaced by z, then y is pushed onto the stack. So we have a little bit of pliability here when it comes to how we consider this third case. So as a result of this, if you're wondering where the top of the stack is, the top of the stack is the symbol on the furthest left. Which at first, for those that are familiar with stacks, this might look a little backwards for you. So the top of the stack will be the leftmost symbol that gets replaced here. So remember, the way transitions work is they operate on the state and the top of the stack, right? So we have to commit to an entire pair. We can't just like mix and match them, right? Just like what we've seen in our example. We can't just mix and match the states and the stack, right? We can't just like, oh, I like this state and I like that stack. No, you have to commit to one of these pairs, and there's only going to be a finite. It's going to be a finite set of these pairs that are possible. So that's what a PDA is.